I'm going to explain the work we have done in collaboration with the University of Parma with the title fatigue assessment in sub-assemblies with aluminum 7075 T651 and scalmalloy. First of all, I would like to explain the origin of this work, that is the result of measured surface stay at the University of Parma during these last months. As all of you know, our research group has been focused on printing fatigue for many years, studying different aspects and conditions that appear in this damage phenomenon. As you know, printing fatigue appears when we have two surfaces pressed together, and somehow they are subjected to some relative displacement between them. A few years ago, we start a new research line focused on a more practical assembly, where we also can good fast threading. That is the sub assembly or a ring fitted design. Here, in this type of assembly, we can find threading at the edge between the shaft and the hub, because at this point we have the contact pressure produced by interference between bodies, the relative displacement between the shaft and the hub due to the movement of the shaft up and down. A former work also suggested the introduction of a toroidal buoy inside the shaft of this sub-assembly in order to make the critical zone more flexible and thus trying to improve the fatigue life of the comfort. And obviously, the only way to manufacture such a toroid would be by additive manufacturing techniques. And this is the reason why in this work we are going to study two materials, aluminum 7075 and scalmalloy. That is a type of aluminum designed for additive manufacturing. Also, in a previous work, in a previous collaboration with our colleagues from Parma, we studied the cylindrical contact pair subjected to also to threading, and we include the rolling effect. The important thing here is that we apply the well-known Carpenter criterion to try to estimate the fatigue life of this assembly. To obtain very good results for both the rolling, taking into account rolling and no rolling. This is the point in which we wonder if we could apply this criterion, that is a stress-based criterion, to our sub-assembly and also include the scalmalloy. Obviously, to apply this criterion, we need the typical properties of fatigue and also the fatigue curve. For the case of aluminum 7075, the fatigue curve is well described. You can find out of the literature, so no more comments on this curve. We have chosen one of them. On the other hand, we need the fatigue curve of the scalmalloy. The good thing is that we have our own fatigue curve with the specimen made by the same manufacturer that will manufacture our cells, thus eliminating one possible variable of the problem. In any case, this curve, the scalmalloy fatigue curve, deserves some more comments, as after doing the test, we analyze the fracture surfaces. We are going to see what type of defects to provoke the initiation of the crack. Something like what Reza saw this morning. You can find that we have surface defects that are defects very close to the surface, and this is an initiation point. We also have internal defects that are defects or voids inside the specimen. These defects normally appear for large lives. And also we have, I have full surface defects, but are the typical initiation that we can find, for example, in aluminum 7075, a crack that initiates from the surface. It is important to note that for this work, I have fit the SNQ only, taking into account this surface depth, or this type of initiation, and the surface depth, avoiding the internal dimension, in order to be more accurate in our sample interest. So to summarize what we are going to do in this work, we are going to design a rig to do some tests with a configuration, something like that, to reproduce the sub-hub assembly. Then we are going to design a FEM model to subtract from the FEM model the stress file, and then we are going to apply the carpentry criterion to predict the crack initiation, orientation, and the fatigue line. So let's start with the experimental campaign. To do that, we design a specific rig only for this type of test, in which we apply a normal load to the shaft instead of reproducing the internal pressure by the interference in a more controlled way. We thought that with these 4 bolts that are instrumented with a load set, we can control better the pressure produced at the contact zone. Also, at the point of the shaft, we apply a bending load with a load ratio of 0.1, thus ensuring that the hot spot will be at the upper part of the shaft. We did 9 tests, 5 with AL7075 and 4 with scalmalloy. All of them with the same normal load. And the bending load, we vary the bending load between 5.4 kilonewtons up to 14 kilonewtons in order to capture all the range of light from 65,000 up to 100. These results will be compared later on with the prediction one. Also, I have included a short video of the performance of the test. I don't know if it works. Yeah. Daniela, could you play in the video? Thank you. It's working. It's right. Yeah, we have the tool that we use to apply this bending force. And after all these tests, we analyze the fracture surfaces. Analyzing the fracture surfaces, we went to a confocal microscope. We locate the initiation point, and at this point, we obtain the topography of the surface in order to draw some different lines to obtain the crack initial path, like the one shown here. These are some measurements for 2 test specimens that are made of aluminum 7075. The orientations range between 15 and 45 degrees, up to a length of 50 microns. The results will be compared later on with the image. Of course, we did the same procedure with the scalmalloy results. In this case, we have to be careful because, as you know here, as you can see here, these are a lot of measurements of the profile for 3 different specimens and some different measurements for each species. More or less, all of them have the same slope, but one of them grows or seems to grow contrary to the direction expected. But this has an explanation. This dashed line is obtained by this line passing through a ball. That is what we can see here. So probably in this position, this is the crack initiation point, and the crack grows goes up and also goes down. However, after this point from 100 micrometers, you can see that the orientation is more or less the same. At this point, I would have liked to show you the measurements for the grain size, but unfortunately, they are done still for many reasons. So I apologize for that, but I'm going to use some values that I have found in the challenge. Of course, we are working on that, and in the future we will have these results. For aluminum 7075, I have used an average value of 35 microns for the grain size, and for scalmalloy, an average value of 7.5 microns. This is important because the model I'm going to apply now, the carpentry model, depends on this part. So up to here, we have defined all the experimental part. Now we move to the numerical part. We have designed this model to reproduce the complete test. We have done one model with a coarse mesh size, 1.2 millimeters. And then we have used the submodeling technique focused on the sum of inputs to be more accurate in the critical zone and decrease the computational time. I have done two submodels. The first one with a mesh size around 3 microns, and the second one with a mesh around 7 microns. That is the order of the grain size of the scalmalloy I have used. Now I'm going to analyze what happens to the first principal stress at the upper generatives. That is where we will find the hotspots. Here we have the results for the coarse mesh, the medium mesh, and the fine mesh. In this graph, we can see the principal stress along the axial direction on the upper generators for the different bending load applied. Of course, the finer the mesh, the largest the values at the hotspots. These dotted lines represent just the edge between the shaft and the hub. As you can see, when we apply the bending load, the spots move slightly inside the column because this very. Okay, so this is like an intermediate step, but we want to use this model, the finest one, to try to predict the orientation and the predicted time. The maximum points of this zone will be the hotspots for the different bending load applied. Now, these hotspots are going to be used to estimate the critical plane. These hotspots that are here, we have put here, will be at the origin of several material planes between 0 degrees and 180 degrees to cover all this area. For each material orientation, we are going to apply this expression. That basically depends on the amplitude of the normal stress to each plane, the mean normal stress to each plane, and the fatigue parameters, the fatigue limit, and the ultimate stress. Evaluating this expression for all the critical planes, the critical plane with the maximum value of this expression will give us the critical plane. Independently of the load applied, sorry, I forgot to say that we are averaging these values along a distance of along a length of 2 times the grain size. Independently of the load, bending load applied, always we obtain a result between 5 and 6 degrees to the vertical. So if we compare this estimation with the measurement, we can see on the left for aluminum 7075 that the beginning maybe the prediction is more or less good, but as we move inside the specimen up to 200 microns is quite different. On the other hand, amazingly, for scalmalloy, the predictions are quite good. This is something for which I have no explanation yet, because I was expecting just the contrary. Better result for aluminum 7075, which is an homogeneous material and we have more control on it, and not for scalmalloy. But this is what I have. I still have to proceed in that. In any case, now we know the orientation of the critical plane, so we move to the light estimation. Knowing the direction of the critical plane, we are going to simply apply the carpentry criterion. That depends, like the expression, on the amplitude of the normal stress to the critical plane, the mean value, also the amplitude of the tangential stress, and some fatigue parameters. It is important to remark that now for this equation, we evaluate these stresses at a distance of 2D, the hot spot, not an average value. It's like a points method or something like that. So after applying this to all our results, we compare our predictions with the estimated results. On the x-axis, we have the experiment results. On the y-axis, the estimation. The dotted lines are scatter 1 for 2 and for 3. All of the results lies inside scatter 1 of 3, and most of them inside scatter 1 of 2. So you can say that the model works well beside the complexity of the whole assembly. So finally, to conclude, I want to say that this is not a finished work. We have to do a lot of things still. But as preliminary conclusion, what I have said, the applied model works well in terms of prediction. In terms of initial graph path, there are remarkable divergences, especially with aluminum 7075. But we have to measure more specimens. And for future work, we have a lot of things to do. We have to measure the grain size, and probably these results will vary slightly. We want to do new tests with different normal loads because all of them have been done with the same load. Of course, and this is mandatory, we want to analyze the fracture surfaces of the scalmalloy specimens because we know that voids can modify the total life and so on. So that's all. Thank you very much for your attention.